in this case DBU, or in the case of potassium phosphate for pyrazoles, is that the base would assist this precursor leading to final products. Okay, this is consistent with other mechanistic proposals involving the role of base in somehow similar transformations mentioned in these reference. The role of the base here is supported by the literature. Okay. So now I discussed, let's say the main concepts, the conceptual background on chemistry. Now I will be a little bit more brief in presenting other examples of these chemistry that we have been able to develop in my laboratory. So we have been interested in cross-coupling aryldiazoacetates with boronic acids under blue light radiation to on the compounds containing the CC bond formation associated with this cross-coupling. In this study, we observed that a very few pairs of aryldiazoacetates and boronic acids they actually work in the dark. The scope is very narrow, and when you actually use blue light radiation, the scope is much broader with generally higher yields, and because of this fact, we call this enhanced blue light radiation, because the scope of the function is much broader when you use light. Okay, so we took a few examples synthesized by this cross coupling, used in synthetic applications for biologically active adenine, ibuprofen, and benactazine, as you can see here. And collaborating Professor Rodrigo Formanich, also from Unicamp, and he did some calculations for us, also studying the difference between the thermal, the reaction in the dark, which is a thermal process, or the chemical process. Or I cannot go into too much details here, but please, those interested in the original publication. We have been able to show or advocate based on our experimental evidence that when the reaction works in the dark, this also likely involves a free carbon. We have been able to trap and generate the proton cycle proper in the dark. Okay. So I have a cover of the journal. I think it's a nice cover. So moving forward, we also studied these insertions of one-3-diketones. So one-3-diketones can cleave or formally cleave this CC bond. So here in the carbon of the aryldiazostate, we have been able to produce a little bit more than 20 examples. In terms of mechanism, we studied a mixture 1-to-1 of symmetrical ketones, here containing two methyl groups, here containing parachlorophenyl groups. Here observe you don't observe crossover products. Okay? You don't observe anything like this. So because you don't observe any crossover, you observe like a mixture 1-to-1 of compound in 60% combined yield. Because you don't observe the crossover, this is a strong argument in favor of intermolecular rearrangement. And we also investigated the reaction of aryldiazoacetates with Silvina ethers, attempting to isolate this sort of cyclopropane that we think is involved in these transformations. However, this compound showed to be unstable and it could still recover the final product. So it's still this supports our mechanism, but we have not been able to isolate. So you just mix, put in the light, and it works. So it's, I was really surprised. It works very well, actually.
So do the reactions have to be done under inert atmosphere? Or you can do them under no?
Just mix, and so sometimes you can see some change in the yield, but it's like 5, maybe 10%. I don't think it justifies doing a freeze pump tour and degassing thoroughly. You don't gain much yield with this.
So another question has come up in the boronic acid paper. Does it work with isoton diazo?
Which sort of diazo, sorry?
It says isoton diazo.
I'm not sure if I'm familiar with this structure.
Someone may have to elaborate or send you a text, I think, with the structure.
Yeah. So please send me an email. If you have access to my email, please send me an email. I'd love to talk more. Yeah, I'm not sure I understand. Sorry.
That's okay. I think, yeah, her bachelor's degree from the National University of Rosario in Argentina and completed her PhD under the supervision of Professor Rolando Spanavello. I'm sorry, my Spanish isn't what it's supposed to be. She did postdoc with Jonathan Goodman at Cambridge in the UK, and then another postdoc in Rosario with Professor Imundo Ruveda. And in 2002, she started working as a research scientist at the National Research Council in Rosario.
The chemistry of boranes, boronic acids and esters, and trichloroboranes. These compounds exhibit good availability, low toxicity, and high synthetic versatility. When I was doing my postdoc in England, I became interested in the Diels-Alder reactions of vinyl boranes. These reactions had been developed by Singleton and co-workers in the 90s and were very interesting because vinyl boranes exhibited high reactivity, regio, and endostereoselectivity due to the presence of the boron atom, which withdraws electron density from the double bond. And also the boron has some secondary orbital interactions in the transition structures for these Diels-Alder reactions. In addition, the properties of vinyl boranes can be rationally designed by the choice of the ligands on the boron atom. And the products of these reactions can be converted into a range of compounds that cannot be accessed directly by Diels-Alder reactions. So we started by doing a theoretical study of this reaction to rationalize all the experimental results. And then when I was coming back to primary carbons, and so the stereogenic centers were too far away from the reactant double bond. And that maybe if we introduce secondary stereocenters directly attached to the boron atom, then we would have higher EEs. We could synthesize boranes like this one by using terpenes like pinene, teucarine, and thiocarine. But although we tried this idea in the lab for a long time, it didn't work. And NMR gave us some hints as what was going on, and we observed some proto-deboronation reactions. And so we believe that the problem was that these boranes were too congested. So after that, then we decided to leave only one chiral ligand on the boron atom and leave one halogen atom also on the boron. This would give more electron deficient and less congested borane. And so we developed this synthetic sequence in the lab in which we prepare the dihaloborane from reaction by the trihaloborane and thiacetylsilane, and then did a single hydroboration reaction to introduce the chiral ligand, and then by using tributyl vinyl tin, we introduce one vinyl group, and then having the dyeing in the reaction media, then we could perform the Diels-Alder reaction at room temperature, and then since the adducts are unstable, they have to be derivatized. In our case, we oxidize them under basic hydrogen peroxide conditions. And in this case, we were very glad to see that we could obtain the products with yields up to 54% and very good endo-exoselectivities, but the EEs were below 40%. So there was some improvement from the previous results, but EEs were still not so good. And we were when we were working with these boranes, we had to use inert atmosphere conditions and had to be very careful. And we became interested in the chemistry of boronic esters. And actually, the Diels-Alder reactions of boronic esters had been developed earlier in the 60s by Matheson and other groups. But we wanted to study this reaction a little further. So we started by studying the reaction of these boronates here with cyclopentadiene, and chose the pinnacle derivative because it showed higher stability and offer operational simplicity. Boronates are more stable than boranes because the oxygens donate electron density into the vacant p orbital of the boron atom, but this brings lower reactivity and selectivity. So we started studying the Diels-Alder reactions of vinyl bipene with all these dienes here, and found that the reactions could be easily performed under microwave irradiation at temperatures between 150 to 220 degrees in short reaction times, and obtained very good yields of the cycloadducts, shown here in blue. But the endo, exo, and retroselectivities were moderate. And we also did a tandem sequence in which we did an oxidation reaction after the Diels-Alder reaction. And this also generated a series of alcohols with very good yields and similar selectivities. After that, we decided to study the effect of substitution at the double bond. So we chose a series of alkynyl boronates. In this case, we observed that the substitution of the double bond reduced the reactivity considerably. And so microwave heating was not practical. So we optimized two different type of conditions, like thermal heating at 170 degrees and bronzed acid catalysis. And from a range of catalysts, we chose TFA as our catalyst at 80 degrees. And most of our compounds reacted very well, giving very good yields of the products. As you can see in red, the yields for the thermal Diels-Alder reactions. And also we obtained very high exoselectivities. But in the case of the two aryl substituted compounds, the yields were very low. They were higher under Bronsted catalysis, but they were still very low. And by doing calculations and further experiments, we realized that these reactions were endergonic, so they were reaching equilibrium. That's why we couldn't get higher yields. So after that, we focused our attention on adenyl boronic ester derived from pinnacle. And even though this compound had been used in many reactions, no one had investigated its use in Diels-Alder reactions. Only the ruthenium catalyzed amidization reaction had been reported. So we first studied the reaction with cyclopentadiene and found that under thermal conditions at 200 degrees, we could obtain the cycloadducts in very good yield, 86%, in a 50-50 endo-exo ratio. But this reaction was completely peri-selective and retroselective. So we only observed 4+2 cycloaddition with an internal double bond. We also proved the versatility of these products with different derivatization reactions, which could be performed in situ, like oxidation to give a mixture of diastereomeric allylic alcohols in very good yield. And we also coupled the Diels-Alder reaction with an elaboration reaction with paranitrophensaldehyde to give a mixture of diastereomeric homoallylic alcohols. We also performed a very thorough theoretical study of this reaction. We studied all the competitive mechanisms and found that the one for the experimentally observed reaction corresponding to the concerted pathway was the most favorable one. And when we were trying to locate the transition structures for the 2+2 cycloadditions, we found structures that connected the 4+2 cycloadduct with the 2+2 cycloadducts. So this corresponded to a formal COPE-3,3 sigma tropic rearrangement. And we are studying the potential energy surface a little further now. And we also found that the competitive radical mechanism was less favorable. During these years, we also became interested in the asymmetric organocatalyzed reactions of organoboron compounds. And the first reaction was described by the Chang group and consisted in the conjugate addition of alkynyl boronates to enols catalyzed by binols. And we did a theoretical study of this reaction and found that transesterification of the initial boronate with a Aryldiol gave rise to this cyclic boronate here, which has such a distorted geometry that the oxygens cannot donate electron density into the vacant p orbital of the boron atom. So it is more Lewis acidic and then can coordinate to the enon and then facilitates the subsequent conjugate addition step. So we thought that maybe we could use this idea for organocatalyzing our Diels-Alder reactions. So we would need a boronate that has that can exchange its ligands. So we used the butanol derivative and thought that maybe we could obtain boronate with enhanced Diels-Alder reactivity. So for this, for the butanol derivative, we need to heat the reaction at 150 degrees for 1 hour and the microwave irradiation. And after oxidation of the cycloadduct, we obtain a 91% yield of the of a 41 to 59 endo-exo ratio of alcohols. So we, in our earlier screening experiments, we tested a series of binols, but unfortunately, they gave similar yields as the background reaction and poor enantioselectivities. And then we thought that we could use mandelic acid for organocatalyzing this reaction. At that time, no one had used hydroxy acids for organocatalyzing organoboron compound reactions, and now it's a well-known procedure. But so we thought about mandelic acid firstly because we were using it as a chiral derivatizing agent for determining the enantiomeric excesses and the absolute configuration of our products for our initial asymmetric reactions, and also because we knew that hydroxy acids combined with boronic acids in different manners. So we were very glad to know that to see that mandelic acid gave a promising higher yield than the background reaction, and that the endoisoselectivity inverted, but the enantioselectivity was not very good, below 20%. And also we noted that if we use the acetate derivative or the methyl ester, the catalytic activities or the reactivities were lower. So we needed both functionalities in the hydroxy acid. Then we screened more acids, and we also optimized the reaction conditions and found that if we use 1.7 equivalent of butanol and did the reaction in the DCM at 70 degrees under microwave irradiations, we could obtain very good yields of the products. And under these smooth conditions, if we use 1 equivalent of mandelic acid, and if we use 0.3 equivalent, we got somewhat lower yield, but we could obtain a 72% yield after 3 hours of heating. And still, mandelic acid was the best hydroxy acid. So this was the first example of an organocatalyzed cycloaddition reaction of a boron-activated compound. We also did a theoretical study of this reaction, and here is the full catalytic cycle, but I want you to focus on the first step in which the initial boronate undergoes transesterification to give this acyloxyborane, and this transformation can also be observed by boron NMR. And this acyloxyborane has a lower energy LUMO, almost 0.8 electron volts lower than the initial boronate, which suggests that this is reactive species. And this species has an activation energy which is 3 kcal per mole lower in energy than the background reaction. We've been trying to optimize this reaction further. We, for instance, we optimize the reactions under conventional heating in a pressure tube and change our derivatization reaction to transesterification with pinnacle to avoid the formation of volatile alcohols, and tried many other new hydroxy acids and sulfonamides as catalysts, but so far we couldn't find a superior catalyst. And we also tried the trifluoroborate as the starting material. Potassium trifluoroborates have been used in organocatalytic reactions of organoboron compounds, like this example from the Thieme Group, in which they use this furan substituted, this boron substituted furan to do a conjugate addition. And we were thinking about this chemistry. We wonder whether we could use these furans as dienes in Diels-Alder reactions. The Diels-Alder reactions of boron substituted dienes had been known for some years. The boron can be introduced at carbon 1, and this gives an boronic boron compound, which then can be submitted to an elaboration reaction with aldehydes to introduce diversity, or either boron can be at carbon 2, which gives an alkenyl boronate, which can be submitted to different reactions like a Suzuki-Miyaura cross-coupling as shown here. So what we wanted to see was the influence of the boron ligands on the reactions of these boron substituted furans, and also the influence of the position. The products of these reactions are very highly substituted and present a bicyclic core that is present in many natural products and other synthetically useful compounds. And these reactions would have many potential applications, like preparation of platform chemicals or self-healing polymers from biomass-derived compounds. And we were very glad to see that when we first tried our first reactions with maleic anhydride as the dienophile, then the reactions worked very nicely when boron was at carbon 3. For all these analogs, we got the exocycloadduct exclusively with yields above 90%, and especially for the potassium trifluoroborate, we've got 99% yield after 5 minutes at room temperature in acetonitrile. And most of these compounds precipitated during the reaction, so they could be easily isolated by filtration and washings. Also, we noticed that if we dissolve these compounds completely, some retro-Diels-Alder could be observed. And in the case of the when the boron was at carbon 2, then we were not able to isolate the products. But in the case of the trifluoroborate, we observed some signals by proton NMR at room temperature corresponding to the product. And then we started studying the reactions with other dienophiles. And in this case, I showed the results for phenylmaledimide. And the reactions were very efficient as well, but they were less exoselective. And we found that selectivity was also very dependent on solubility. For the potassium trifluoroborate, if we did the reaction in acetonitrile, we obtained 100% yield of a 28 to 72 endoexo mixture. While when we performed the reaction in DMF, it took 6 hours and gave the products with 95%, but with a 5 to 95 endoexo mixture. And in this case, we're very happy to see that we could obtain the products when the trifluoroborate was at carbon 2. And this reaction takes much longer. It takes 5 days to give a 70% and 10 days to give an 82%, but it gives the exocycloadduct exclusively. And the reactions for these dienophiles seem to be less reversible. We also explore some strategies for improving the selectivity and the reactivity. For instance, for the trifluoroborate at carbon 3, we observed that if we change the cation from potassium to tetrabutyl ammonium, which can be done very easily in the lab, then this compound is much more soluble, and then the reaction can be performed easily in 1 hour at room temperature, giving the exocycloadduct exclusively with a 99% yield. And also for the BPIN analog, which is much less reactive, the reaction has to be performed at 80 degrees. If we coordinated a fluoride to the pinnacle boronate, then, and this can also be done very easily in the lab and can be monitored by boron NMR, then the reaction only takes 1 hour at room temperature, giving the exocycloadduct exclusively in quantitative yield. And then after that, the fluoride can be decoordinated by washing with water. So we did some theoretical calculations to explain these results and found that trifluoroborates exhibited the lowest free energy barriers, and also that the reactions for the 2 boron-substituted furans were endergonic, and the reactions with phenylmaleiamide were more favorable than those for maleic anhydride. And we also been trying to develop some derivatizations like epoxidation using methylchloroperbenzoic acid for the trifluoroborate, oxidation to the ketone using ozone, Suzuki-Miyaura cross-coupling under conventional conditions to introduce a phenyl group here, and we are still trying to optimize the conditions to aromatize this ring. Finally, I would like to mention some of the problems that Gary already commented. So doing scientific research in Argentina and many other Latin American countries is not easy. A lot of progress has been achieved in the last decades, but we still face many difficulties like shortage of funding, insufficient infrastructure, access to equipment, reagents, and literature, difficulties with imports, and also distance to developed countries impacts on interaction with colleagues, assistance to conferences, and access to reagents. And so all actions from governments and institutions are very important to support the development of scientific research in this region. So I thank Thieme again for organizing this webinar. And you for your attention. And finally, I would like to acknowledge all the members of my group, past and present, former co-workers and collaborators, and all my mentors, Rolando Spanevelo, Jonathan Goodman, and Mundo Rúbeda, and all these agencies which have supported my research over the years. And I'll be happy to answer any questions.
Thanks so much, Silvina, for a great seminar and tour de force on boron chemistry, some of which I recognized a little bit. So there is a question from one of the participants. Have you tried the Amide-boronates, and do they provide any advantages in terms of selectivity?
I guess they are asking about the Diels-Alder reactions, right?
It just says, yeah, it doesn't say, but I imagine, yes.
Yes, yes, the Amide-boronates work very well too. So in these years, I didn't want to go into further detail because of the time restriction, but the trifluoroboronates is the most reactive one. It reacts at room temperature only in 15 minutes. And then the rest of the analogs are less reactive. For instance, the bpin has to be heated at 80 degrees. The bimida has to be heated at 40 degrees. And the acid takes, all these compounds take around 1 day at different temperatures, room temperature, 40 degrees, and 80 degrees. So, but for us, it was really convenient to work with trifluoroborates. This was our one of our first experience with trifluoroborates, but they were really nice in the lab.
One question, I was just playing a little bit on paper. Is there any derivative of sulfoximines that you could make of boron? I don't know if any have been made of, using the NH bond to make a bond to the boron, and it would be chiral. So have you ever thought about sulfoximine derivatives to make complexes with boron?
No, we haven't actually, but that's a really nice idea. Yeah, we haven't tried that. Yeah, it's a nice idea. It would be very interesting to try.
There's another question from a participant. Have you tried any chiral 1,2 diols for the enantioselective reaction?
Well, the diols we tried were the vinyls derivatives, biphenyls derivative. So yeah, we didn't try any other type of chiral diols so far, yeah. But I mentioned that these were initial screening tests, so I didn't go into detail, but our initial tests were at room temperature, and we ran our reactions for 6 days. And so the yields were not very good. But then after optimizing our reaction conditions, we tried our vinyls again and found that still hydroxyacids had showed higher yields. We think there is a problem related to transesterification. So even though the vinyls have been used in many organocatalytic reactions with organoboron compounds, these reactions, once the cyclic boronate forms, it's so acidic that when can coordinate to an heteroatom, then the reaction goes really fast. In our case, we don't have an heteroatom to coordinate in the Diels-Alder reaction. So if transesterification is being a problem, then we don't have something pushing to go further. But yeah, we didn't, we only tried with biphenyls.
Okay. So one question I had was a lot of the vinyl boronate esters polymerize easily. Do you use a large excess of the vinyl boronates, or it's
no, not really. Well, I think not for the ones we were using. I know that the vinyl boronic acid polymerizes, but these all the esters we have used and all the esters I have shown during my whole presentation don't have that problem. Not for boronic, these boronic esters. Not for sure. Not for the alkynyl bipins or the or either the butanol derivatives.
Okay. There's another question. I'm not sure I understand this one, but it says, have you had success with chiral boronic esters? Seems like the logical succession of your work. So I'm not sure I understand. This is from Gerardo Morales.
So chiral boronic esters?
That's what it says, yes.
Yes, well, there were some reports on the use of chiral boronic esters. Like one of the earliest reports I remind of is the use of boronic ester derived from tartaric acid. But that doesn't give very high EEs either.
Okay.
I think now, after all this chemistry being developed, then if we can develop an organocatalytic version of this reaction, would be much nicer than using stoichiometric conditions.
Okay.
But I didn't mention that either when I said that we kept trying optimizing this. At the alpha carbon, and then also use sulfonamides, but they didn't work very well.
Okay. So Todd Martyr wants to know if you ever tried vinyl B-neopentyl compounds.
So sorry, say that again, please. Vinyl?
Yeah, the neopentyl boronates.
No.
Those are more Lewis acidic than the B pins.
Okay, yeah, no, we haven't tried that.
Okay.
Yeah, but as Igor said, if anyone wants to ask me further questions, then please send me an email and I'll be happy to answer them.
Okay. Any more questions? Going once, twice? Okay, let's thank Silvina again for a great seminar and introduction to boron chemistry calculations and Diels-Alder reactions.
Thank you.
Okay, so moving along, we will now have the final talk of the series from Marcio Paixão. So Marcio.
Gary, sorry, we're just going to have a short interlude and show us about science of synthesis.
I got screwed. I was so excited about having Marcio talk that I forgot.
Sorry about that. Just checking, is that visible?
Yes.
As okay. Let me just check.
Working with catalytic and anti-selective methods. He started a postdoc at Sao Paulo, then moved to Aarhus in Denmark, where he worked with Carl Anker Jorgensen, and then started his independent career at the Federal University in São Carlos in Brazil. He did a short sabbatical as a visiting professor in the group of Carlos Barbas at Scripps, and also a sabbatical research stay with Dean Tost at Berkeley. And so today he's going to talk to us about practical and selective protocols for the preparation of amide-containing molecules. Marcio, we're looking forward to it.
So thank you very much, Professor Molander, for this kind of introduction. I would like also to thank Thieme and Science of Synthesis for the opportunity to participate of this WebCheminar, present part of our research program, especially the research related to the photocatalytic preparation of the amide-containing molecules. So before to start, I just wanted to talk a little bit about who are we and where do we work. Well, we are a synthetic group, organic group, with research interests focused on the development of new methodologies, ranging from stereoselective transformations, especially on the stereoselective isocyanide-based multi-component reactions, to the design of new materials for biomass valorization. And recently, we are falling in love amides. Amides containing drugs and agrochemicals have also been explored and designed successfully over the years. So it's not a coincidence that reactions involving amide formation represent one of the most carried out transformations in pharmaceutical industry. Although significant advantage has been made for the direct synthesis of amides, established routes remain based on the CN bond formation. Traditionally, the principal route for the synthesis of the amides is represented here, where you can see the direct condensation of an amine with the carboxylic acid in order to generate the amide. But of course, we would need a coupled agent to promote this. These chemicals for many purposes. These metals suffer from poor autoeconomy and are often incompatible with sterically congested amides. Consequently, a search for a broad catalytic amidation strategy has been pursued over the years. And here at this box, you can see some of the methodologies already described for this, and where I would like to highlight some of them. Some fundamental advances include, for example, organoboron derivatives using as a Diels-Acid to promote the activation of the carbonyl system. So, and others with organometallic and organic or organic catalytic protocols. So, however, the CC disconnections to install the amide bonds offer a new synthetic strategy to incorporate the amide moiety to a chemical scaffold. So there are different ways to do that, and one that should be highlighted is the use of the multi-component isocyanide-based reactions. There's the UGI or the Passerino, where you use the isomide. Use of UV radiation heat, or sometimes they use a radical initiators, which are with suitable acceptor substrates. So here is some representative systems that generate the carbomolecule under harsh reactions conditions. On the other hand, there are different systems and which are suitable substrate to generate the carbomolecule radical under low energy. Under these conditions, the carbomolecule radical have been accessed through hydrogen atom transfer mechanism, when formamides are used, or oxidative systems, oxidative procedures, or reductive protocols. Among these precursors, like hydropyridines, has been recently applied in carbomolecule radicals generation. Single electron oxidation and visible light radiation in the presence of suitable photocatalysts to provide the corresponding radical after fragmentation. In 2020, the groups of Melchiors and Jacob von Wangelen explored the use of the hydropyridine derivatives as alternative strategies to the carbomolecule radical generation for further installation of these amide bonds on hetero-aryl bromide, as reported by Melchior. and active olefins, as reported by Organoboron groups. Most recently, by the exploration of electron donor acceptor, EDA complex formation with the hydropyridine. Hong group disclosed the cross-coupling reactions using any amidopyridinium compounds, which includes in the scope examples of C4 carbonated pyridines. So, inspired by these findings, we rationalize that an unprecedented photocatalytic carbonylation of which you can see that's a non-proteinogenic amino acid, a new type of non-proteinogenic amino acid that may be used in future as a therapeutic derivatives. So we found in literature some applications of these dipoles in photocatalyzed additions, so we then explore their activity as a radical acceptor. So our study began with the using of azomethylamine derived from benzaldehydes and the cyclohexyl amine derivatives, dihydropyridine, as a model substrate, and by evaluating the reaction conditions or the parameters of these reaction conditions, we identify that the use of only 1% of the photocatalyst, we are able to obtain the corresponding product in high yield, 70% yield, having acetonitrile as a solvent and 456 nanometers blue light emitting diode lead in radiation. So many other modifications of these reactions parameter, such as solvent change, concentration, and also the addition of additives did not improve the reaction outcome. So based on these control experiments and also previous report, we rationalize a plausible reaction mechanism. The photocatalyst here indicated the 4-CZIPN, and this photocatalyst efficiency is converted to this long-lived triplet excited state, which is oxidized enough to promote the single electron transfer oxidation of the dihydropyridine. So after fragmentation, generate the carbonyl radical, and this carbonyl radical is added to the iminion ion and give rise to the intermediate B. So furthermore, this reactive intermediate undergoes single electron transfer reduction with the reduced photocatalyst to provide after protonation the desired product. So these works have been developed by Marcio, and I have published these results in 2021. So with the optimal reaction condition in hands and also with mechanism elucidation, we began to evaluate the scope of this transformation for a range of aryl-azomethylamines. And as you can see in this slide, aryl-azomethylamines bearing either electron withdrawing substituents or electron donated groups underweight carbonylation with the cyclohexyl derivatives, the hydropyridines, in moderate to good yields. So here's in this part, you can see all of this result. Importantly, substrates containing aryl bromides could successfully tolerate. It's good because it's this functional group, the further functionalization by transition metal mediated cross-country reactions. Other substitution partners do not show any substitute influence on the reaction outcome, and notably ortho and meta substitution is well accepted under this transformation. So likewise, pyridine and furans, which are privileged pharmacophores, were also competent towards the carboxyl radical installation. And the azomethylamines bearing phenyl substituent on the pyrazolidinone ring is also compatible with example 15. However, the product is generating a 1-to-1 DR. Bianca, in order to demonstrate the method applicability in late-stage functionalization of dense molecules, she prepared a substrate derivative from etodolac, which are an anti-inflammatory drug. This substrate possesses a benzyl CH bond and an acidity and H bond, which are known to interfere with radical pathways. To our delight, subjecting this substrate to the reaction conditions, we are able to assess the desired product in excellent yield. So here are some other examples that we are able to produce by using this methodology. And as you may expect, the growing application of the modifier peptides as drug candidates led us to evaluate the feasibility of this development disease Light-Mediated protocol in the direct installation of proteinogenic amino acids across the azomethyl imine scaffold. Such a combination allows the synthesis of non-natural amino acids and the assembly of modified peptides in a single event. To our delight, the reactions tolerate a range of amino acid derivatives, including those containing non-polar side chains, polar, uncharged, and aromatic systems, which could be smoothly transformed in good chemical yields. Likewise, non-proteinogenic amino acids from L-phenylglycine and 2-methylalanine were nicely incorporated in this azomethyl imine.
欢迎参加网络研讨会，您的参与身份为处于仅收听模式的参与者。
Trap this radical, this nucleophilic radical via Geisel addition and generating this unnatural N-forces asparagine. So here it's some of the products that we can generate via this chemistry. And it's quite broad scope in terms of amino acids. When the amino acids are present in the hydropyridine under photocatalytic conditions, blue red, and forces CZIPN as a photocatalyst. This type of product can be generated in good to excellent blue, so we can insert this amino acid side chain into these systems. So another example that I would like to highlight is the possibility to introduce just bioconjugated handles, this proparativity, and also this azide, which can be further used for click chemistry, for example, and then you can think in the application of these systems in conjugation reactions. So we are also able to conjugate commercially available drugs, natural products, and three peptides. So you can build up peptides containing non-natural residues using this chemistry. So these peptides and tripeptides were introduced to the hydroalanine side chain in 30% and also 70% and 68% of yield. So many other variations can also be done using this protocol. And here, what we did, we varied the position of the hydroalanine, so the hydroalanine can be present in a small peptide in the final C, or even in the middle of side chain. So in both cases, these modified peptides could be obtained in good yield only. Low yield were obtained when the hydroalanine are present in the middle of the peptide side chain. So we can also produce these non-natural amino acids in a diastomeric way. So by using this chiral back with alkenes, we are able to produce the amino acid with good diacetyl selectivity, ranging from states 2 to 20 to 1, as you can see at this slide. Here is the mechanism of this reaction. Is almost pretty the same. We have the excitation of the photocatalyst with oxidized the hydropyridine, and then which collapse, generating the carbonyl radicals, which add to the hydroalanine, generate this radical intermediate, which then is reduced by the reducing form of the photocatalyst, generating the photocatalyst for the catalytic cycle, when generating this carbonium here, which is further protonated in the system. So as a final remark, these results also contribute to this statement that the hydropyridine is proven to be an efficient source of amide synthesis under photocatalytic conditions, with the most that are robust photocatalytic conditions and their flow strategies promote the amidation of nitrons, and the batch condition, we can do the amidation of the isomethylamines and also the amidation of the hydroalanine through the CC coupling. And continuous conditions are amenable to the late stage functionalization and modification of new biomolecules, natural products, and other drugs. So what is still open in this field, in my view, is the symmetric version, that it still need to be better designed and improved. So I'd like to acknowledge once again the research group, people who does this chemistry, Thieme, SOS, and also the chemistry department at the Federal University of São Carlos. Of course, that this acknowledgement is also extend to the financial support, CNPq, FAPESP, and Sindicatários, Flora, GSK, and also the Center of Excellence of Research in Sustainable Chemistry. So just here I highlighted some of the collaboration that the group has, and with Daniel Rivera from the Havana University, and also Professor Marco Ferreira from the UFSCar, and Alexander Fernandez de Gato from the Universidad de Concepción in Chile, some of our Latin America and South America collaborations. So I'd like to thank you for your kind attention. I will be happy to get any questions. Thank you very much.
Thanks so much, Marcio, for that great talk. And there are some questions for you, so I'll start off with those. The first one's kind of a tough one, I think. It says, in your experience, what is the best method to synthesize amides to obtain the best yields of the reaction?
For which proposal?
Yeah, exactly.
Because in my point of view, it's all of these methods are complementary.
Yeah.
So you cannot exclude anyone.
Yeah.
Of course, for peptide chemistry, you're still gonna use the traditional coupling.
No. Yeah, as I said, that's a tough question. Another question, in your dipeptide case, do you observe some DR from the product? And is the asymmetric version of this transformation considered?
Yeah, it's the diazoactivity in all of these in all of these chemistries. It's when it's the chiral, the chirality is centered on the radical acceptor, then control, otherwise it's difficult. So of course that you can plan and design asymmetric catalysis using this radical approach and this carbonegative in a good topic of research to do in future.
Okay. A third question from someone I know quite well, Mayra Coutinho in Rio. Did you try to use an aromatic amide radical source in the first and second examples? And if yes, what were the observed results? So an aromatic amide radical.
Yeah, there is one example that we did, and the reaction works on the azomethyl amine as a radical acceptor.
Okay. Let me see if there are any more questions I'm looking through. Okay, so just to clarify the earlier amide synthesis question, Jorge Patino meant amide synthesis for the purpose of functionalizing other molecules. Yes, I don't know. It's kind of hard. So this has to do with the best method to synthesize amides.
Rho, and consequently we can apply with enzymes or antibodies or proteins and other active systems. So, but if the question is, can we prepare peptides using this chemistry? For some examples, yeah. But of course, that traditionally the coupling of peptides is it's well known, and there are some issues, but there's still a lot to be done on this chemistry before to say such a, or to affirm something like this. It's impossible to. In my opinion, I don't like to compare things. I like to say that they are complementary.
Yeah. But it's amazing how far things have come in the past few years, right? I mean, as I look back and thinking about what one could do, let's say 10 years ago with amide bond formation versus now, I mean, it's unbelievable. So there's another question: which one is better precursor for the generation of carbamyl radical?
I didn't get the first precursor.
I think it's the N-hydroxythalamide ester, or DHP, precursor for the generation of carbamyl radicals. So there's, I think, the redox active esters, or DHP.
Depends on your catalyst system, because one you generate by oxidative quenching, and another one by reductive quenching. So it's depend on your catalyst cycle, and you can design with each one. It's depend on the reaction that you're going to apply.
Right.
But in order to prepare, I do think that the active ester is easy to prepare. I have to ask them this question to the students, but I think they you answer that the active ester it's easy to prepare.
Yeah, you always have to ask the students, because they're the ones that are in the lab.
Yeah, although the hydropyridine it's also easy because it's a multi-component reaction. It's ester synthesis, so it's not a big deal to prepare as well.
I have a question about the flow chemistry. So in all your examples, was everything homogeneous throughout the reaction to do the flow chemistry?
Yeah, under this concentration and dichloromethane, yes, that's why we transferred acetonitrile from the batch to dichloromethane to increase the solubility of the system. But we have problems with the instability in this chemistry as well. And another problem that I've not mentioned, but it's the dimerization of the carbomoyl radical. It's also observed in batch, and in flow we avoided the radical dimerization.
Yeah. So are there any more questions from anyone? I see none. So I'd like to take this opportunity to thank Marcio for a fabulous presentation, and all of our speakers today. As I said, you know, there's a long history of great science in Brazil and Argentina, South America. And I think chemistry in Latin America is in good hands with a young crowd that presented today, and many others. And it's always a pleasure for me to visit Brazil and Argentina. Wonderful people, wonderful training for the students. I've had just extraordinary students, as I said, and postdocs from both countries, and I wish all of you the best. And hopefully, you know, we'll get the resources down there under some government at some time that can you know, bring everything along, because there's nothing stopping you from doing great science other than the resources, I think. So I don't know if Fiona wants to say anything, or.
Yeah, I mean, thanks to everybody this afternoon. It's been really great. I've been handed one question to ask each of the panelists. So what is the biggest misconception about organic chemistry? So who would like to go first? Can take it.
No one. Oh, I think it's a usual thing that you never hear about the good things and all the problems we're solving, the enormous problems we're solving, but you hear about everything that when something goes wrong. And I mean, this has been stated before. It's nothing new that I think we're not good.
Most reagents take more than 3 months to get here, so it takes a lot of planification, and even some reagents cannot be shipped to our countries. So yeah, we even have more difficulties here. But yeah, reactions are not. Sometimes they do work very easily, but that's not the most common case, I think.
Mm-hmm. Very good. Marcio?
Yeah, I would say the same word as Silvina. It's people say when we are lecturing that organic chemistry it's so difficult. No, it's easy. We just need to get some insights, and then we can solve. Another thing that we say a lot of in Brazil that, hey, this product is without chemistry. So come on, how this is possible? It's necessary to do things to prepare all of these ingredients, and not only for cosmetic, for example, but also for bioactive molecules that we take when you have a headache after a barbecue. So,
yeah. Okay.
So this is, I think, is the message that we should pass to our students in Brazil. And another point that Silvina also mentioned, in that we do have difficulties to get some chemicals and facility in South America, not only in Brazil. But I think that it's time to strengthen our collaboration in South America, because some things that we do not have in Argentina, we have here, and the other area around it's also true. So we have the Mercosur. We have to do the Mercosur for collaboration as well. So then we can strengthen our initiatives here in Brazil and Argentina and other countries in South America, Chile, Bolivia, Peru, and others.
Yeah. Mm-hmm. Igor?
Yeah, so of course I agree with all the opinions shared here. So my opinion here, if I can add something, but I don't think it's a huge contribution here on the discussion. But in terms of laboratory skills, I would say now thinking more about the work properly done, and in addition to all the comments performed. So for the students and practitioners of organic chemistry, I think it's really important to be very strong in both theory and experimental work. So I hope this is not a misconception, but I think we cannot get around being only very good in theory, but very bad in experimental work, or very good experimental work and not knowing enough about the theory. So I think you have to be as strong as possible, as well educated and skilled in both parts of the science. And it's very challenging and demanding, and it's a great challenge. But yeah, I think the misconception not to think you can overcompensate one by the other. I think both are really important.
Mm-hmm. Okay, so thanks very much, and thanks Gary for moderating the talks today. That's great, and Marcio, Igor, and Silvina for wonderful talks. Also thanks to Gabrielle for joining us as well. And I'd also like to say thanks to Dr. Shomo Sakar, who's done all of the organization behind the scenes, and Dr. Toby Reeve as well, who's been taking care of the chat. And of course, to everybody in the audience, thanks for joining us, and make sure to join us again on May 11th for the CH Functionalization Chem webinar as well. So thank you and have a good evening.
Ciao, everybody.
Thank you. Bye-bye.
Bye-bye.